Chapter 11 Three-Dimensional Geometry. Introduction. In this chapter, we shall study the direction cosines and direction ratios of a line joining two points and also discuss about the equations of lines and planes in space under different conditions. Angle between two lines, two planes, a line and a plane. Shortest distance between two skew lines and distance of a point from a plane. Most of the above results are obtained in vector form. Nevertheless, we shall also translate these results in Cartesian form, which at times presents a more clear geometric and analytic picture of the situation. Direction cosines and direction ratios of a line. If a directed line L passing through the origin makes angles alpha, beta and gamma with x, y and z axis respectively, called direction angles, then cosine of these angles, namely cos alpha, cos beta and cos gamma, are called direction cosines of the directed line L. If we reverse the direction of L, then the direction angles are replaced by their supplements, that is pi minus alpha, pi minus beta and pi minus gamma. Thus, the signs of the direction cosines are reversed. Note that a given line in space can be extended in two opposite directions, and so it has two sets of direction cosines. In order to have a unique set of direction cosines for a given line in space, we must take the given line as a directed line. These unique direction cosines are denoted by L, M and N. Any three numbers which are proportional to the direction cosines of a line are called the direction ratios of the line. If L, M, N are direction cosines and A, B, C are direction ratios of a line, then A is equal to lambda L, B is equal to lambda M and C is equal to lambda N for any non-zero lambda belongs to R. Let A, B, C be direction ratios of a line and let L, M and N be the direction cosines of the line. Then L upon A is equal to M upon B is equal to N upon C is equal to K, say K being a constant. Therefore, L is equal to AK, M is equal to BK, N is equal to CK. Equation 1. But L square plus M square plus N square is equal to 1. Therefore, K square into A square plus B square plus C square is equal to 1. Or K is equal to plus or minus 1 upon square root of A square plus B square plus C square. Hence, from 1, the direction cosines of the line are L is equal to plus or minus A upon square root of A square plus B square plus C square. M is equal to plus or minus B upon square root of A square plus B square plus C square. N is equal to plus or minus C upon square root of A square plus B square plus C square, where depending on the desired sign of K, either a positive or a negative sign is to be taken for L, M and N. For any line, if A, B, C are direction ratios of a line, then Ka, Kb, Kc, where K is not equal to 0, is also a set of direction ratios. So, any two sets of direction ratios of a line are also proportional. Also, for any line, there are infinitely many sets of direction ratios. Relation between the direction cosines of a line. Consider a line RS with direction cosines L, M, N. Through the origin, draw a line parallel to the given line and take a point P, X, Y, Z on this line. From P, draw a perpendicular PA on the x-axis. Let OP is equal to R. Then cos alpha is equal to OA upon OP is equal to X upon R. This gives X is equal to LR. Similarly, Y is equal to MR and Z is equal to NR. Thus, X square plus Y square plus Z square is equal to R square into L square plus M square plus N square. But X square plus Y square plus Z square is equal to R square. Hence, L square plus M square plus N square is equal to 1. Direction cosines of a line passing through 2 points. Since one and only one line passes through 2 given points, we can determine the direction cosines of a line passing through the given points P, x1, y1, z1 and Q, x2, y2, z2 as follows. Let L, M, N be the direction cosines of the line PQ and let it makes angles alpha, beta and gamma with the x, y and z axis respectively. Draw perpendiculars from P and Q to xy plane to meet at R and S. Draw a perpendicular from P to QS to meet at N. Now, in right angle triangle P and Q, angle PQN is equal to gamma. Therefore, cos gamma is equal to NQ upon PQ is equal to Z2 minus Z1 upon PQ. Similarly, cos alpha is equal to x2 minus x1 upon PQ and cos beta is equal to y2 minus y1 upon PQ. Hence, the direction cosines of the line segment joining the points P, x1, y1, z1 and Q, x2, y2, z2 are x2 minus x1 upon PQ, y2 minus y1 upon PQ, z2 minus z1 upon PQ, where PQ is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Example 1. If a line has direction ratios minus 18, 12, minus 4, then what are its direction cosines? Solution. The direction ratio of the given lines are minus 18, 12, minus 4. Therefore, A is equal to minus 18, B is equal to 12, C is equal to minus 4. Therefore, A square plus B square plus C square is equal to minus 18 square plus 12 square plus minus 4 square is equal to 324 plus 144 plus 16 is equal to 484. Let the direction cosines of a line be L, M, N. Then L is equal to A upon square root of A square plus B square plus C square is equal to minus 18 upon square root of 484 is equal to minus 18 upon 22 is equal to minus 9 upon 11. M is equal to B upon square root of A square plus B square plus C square is equal to 12 upon square root of 484 is equal to 12 upon 22 is equal to 6 upon 11. N is equal to C upon square root of A square plus B square plus C square is equal to minus 4 upon square root of 484 is equal to minus 4 upon 22 is equal to minus 2 upon 11. Hence, the direction cosines of a line are minus 9 upon 11, 6 upon 11, minus 2 upon 11. Example 2. Find the direction cosines of the line passing through the 2 points minus 2, 4, minus 5 and 1, 2, 3. Solution. We know the direction cosines of the line passing through 2 points P, x1, y1, z1 and Q, x2, y2, z2 are given by x2 minus x1 upon pq, y2 minus y1 upon pq, z2 minus z1 upon pq, where pq is equal to square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Here p is minus 2, 4, minus 5 and q is 1, 2, 3. So pq is equal to square root of 1 minus minus 2 whole square plus 2 minus 4 whole square plus 3 minus minus 5 whole square is equal to square root of 3 square plus minus 2 square plus 8 square is equal to square root of 9 plus 4 plus 64 is equal to square root of 77. Thus, the direction cosines of the line joining two points is 3 upon square root of 77 minus 2 upon square root of 77, 8 upon square root of 77. Equation of a line in space. We shall now study the vector and Cartesian equations of a line in space. A line is uniquely determined if number 1. It passes through a given point and has given direction, or number 2. It passes through two given points. Equation of a line through a given point and parallel to a given vector, vector B. Let vector A be the position vector of the given point A with respect to the origin O of the rectangular coordinate system. Let L be the line which passes through the point A and is parallel to a given vector, vector B. Let vector R be the position vector of an arbitrary point P on the line. Then vector AP is parallel to the vector, vector B. That is, vector AP is equal to lambda vector B, where lambda is some real number. But vector AP is equal to vector OP minus vector OA. That is, lambda vector B is equal to vector R minus vector A. Conversely, for each value of the parameter lambda, this equation gives the position vector of a point P on the line. Hence, the vector equation of the line is given by vector R is equal to vector A plus lambda vector B, where lambda belongs to R, equation 1. Derivation of Cartesian form from vector form. Let the coordinates of the given point A be x1, y1, z1 and the direction ratios of the line be A, B, C. Consider the coordinates of any point P be x, y, z. Then vector R is equal to xi cap plus yj cap plus zk cap. Vector A is equal to x1 I cap plus y1 j cap plus z1 k cap. And vector B is equal to ai cap plus bj cap plus ck cap. Substituting these values in 1 and equating the coefficients of I cap, j cap and k cap, we get x is equal to x1 plus lambda a, y is equal to y1 plus lambda b, z is equal to z1 plus lambda c, equation 2. These are parametric equations of the line. Eliminating the parameter lambda from 2, we get x minus x1 upon a is equal to y minus y1 upon b is equal to z minus z1 upon c. Equation 3. This is the Cartesian equation of the line. Example 1. Find the vector and the Cartesian equations of the line through the point 5, 2, minus 4 and which is parallel to the vector 3i cap plus 2j cap minus 8k cap. Solution. We have vector A is equal to 5i cap plus 2j cap minus 4k cap and vector B is equal to 3i cap plus 2j cap minus 8k cap. Therefore, the vector equation of the line is vector R is equal to 5i cap plus 2j cap minus 4k cap plus lambda into 3i cap plus 2j cap minus 8k cap. Now, vector R is the position vector of any point P, X, Y, Z on the line. Therefore, xi cap plus yj cap plus zk cap is equal to 5i cap plus 2j cap minus 4k cap plus lambda into 3i cap plus 2j cap minus 8k cap is equal to 5 plus 3 lambda into I cap plus 2 plus 2 lambda into j cap plus minus 4 minus 8 lambda into k cap. Eliminating lambda, we get x minus 5 upon 3 is equal to y minus 2 upon 2 is equal to z plus 4 upon minus 8, which is the equation of the line in Cartesian form. Equation of a line passing through two given points. Let vector A and vector B be the position vectors of 2 points A, x1, y1, z1 and B, x2, y2, z2 respectively that are lying on a line. Let vector R be the position vector of an arbitrary point P, x, y, z. Then P is a point on the line if and only if vector AP is equal to vector R minus vector A and vector AB is equal to vector B minus vector A are collinear vectors. Therefore, P is on the line if and only if vector R minus vector A is equal to lambda into vector B minus vector A, or vector R is equal to vector A plus lambda into vector B minus vector A, where lambda belongs to R. Equation 1. This is the vector equation of the line. Derivation of Cartesian form from vector form. We have vector R is equal to xi cap plus yj cap plus zk cap. Vector A is equal to x1i cap plus y1j cap plus z1k cap. And vector B is equal to x2i cap plus y2j cap plus z2k cap. Substituting these values in 1, we get xi cap plus yj cap plus zk cap is equal to x1i cap plus y1j cap plus z1k cap plus lambda into x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. Equating the like coefficients of I cap, j cap, k cap, we get x is equal to x1 plus lambda into x2 minus x1, y is equal to y1 plus lambda into y2 minus y1, z is equal to z1 plus lambda into z2 minus z1. On eliminating lambda, we obtain x minus x1 upon x2 minus x1 is equal to y minus y1 upon y2 minus y1 is equal to z minus z1 upon z2 minus z1, which is the equation of the line in Cartesian form. Example 1. Find the equation of the line which passes through the point 1, 2, 3 and is parallel to the vector 3i cap plus 2j cap minus 2k cap. Solution. Line L passing through the point A of vector A is equal to 1, 2, 3 and it is parallel to vector B is equal to 3i cap plus 2j cap minus 2k cap. Therefore, A of vector A is equal to I cap plus 2j cap plus 3k cap and its direction is vector B. Therefore, vector equation of the line vector R is equal to vector A plus lambda vector B, where lambda is arbitrary constant, lambda belongs to R. Therefore, vector R is equal to I cap plus 2j cap plus 3k cap plus lambda into 3i cap plus 2j cap minus 2k cap. Example 2. The Cartesian equation of a line is x minus 5 upon 3 is equal to y plus 4 upon 7 is equal to z minus 6 upon 2. Write its vector form. Solution. The Cartesian equation of the line is x minus 5 upon 3 is equal to y plus 4 upon 7 is equal to z minus 6 upon 2. Comparing this equation with x minus x1 upon a is equal to y minus y1 upon b, we have x1, y1, z1 is equal to 5 minus 4, 6 and a, b, c is equal to 3, 7, 2. That is, a line passing through the point A of vector A is equal to 5 minus 4, 6 is equal to 5 cap minus 4 cap plus 6 cap, and its direction is vector B is equal to 3 cap plus 7 cap plus 2 cap. Therefore, vector equation of the line vector R is equal to vector A plus lambda vector B, where lambda belongs to R. Therefore, vector R is equal to 5 cap minus 4 cap plus 6 cap plus lambda into 3 cap plus 7 cap plus 2 cap. Angle between two lines. Let L1 and L2 be two lines passing through the origin and with direction ratios A1, B1, C1 and A2, B2, C2 respectively. Let P be a point on L1 and Q be a point on L2. Consider the directed lines OP and OQ as given in figure. Let theta be the acute angle between OP and OQ. Now, recall that the directed line segments OP and OQ are vectors with components A1, B1, C1 and A2, B2, C2 respectively. Therefore, the angle theta between them is given by cos theta is equal to modulus of A1 A2 plus B1 B2 plus C1 C2 upon square root of A1 square plus B1 square plus C1 square into square root of A2 square plus B2 square plus C2 square. Equation 1. The angle between the lines in terms of sin theta is given by sin theta is equal to square root of 1 minus cos square theta is equal to square root of 1 minus A1 A2 plus B1 B2 plus C1 C2 whole square upon A1 square plus B1 square plus C1 square into A2 square plus B2 square plus C2 square is equal to square root of A1 square plus B1 square plus C1 square into A2 square plus B2 square plus C2 square minus A1 A2 plus B1 B2 plus C1 C2 whole square whole upon square root of A1 square plus B1 square plus C1 square into square root of A2 square plus B2 square plus C2 square. Sin theta is equal to square root of A1 B2 minus A2 B1 whole square plus B1 C2 minus B2 C1 whole square plus C1 A2 minus C2 A1 whole square upon square root of A1 square plus B1 square plus C1 square into square root of A2 square plus B2 square plus C2 square. Equation 2. If instead of direction ratios for the lines L1 and L2, direction cosines namely L1, M1, N1 for L1 and L2, M2, N2 for L2 are given, then 1 and 2 takes the following form. Cos theta is equal to modulus of L1 L2 plus M1 M2 plus N1 N2 as L1 square plus M1 square plus N1 square is equal to 1 is equal to L2 square plus M2 square plus N2 square. Equation 3. And sin theta is equal to square root of L1 M2 minus L2 M1 whole square minus M1 N2 minus M2 N1 whole square plus N1 L2 minus N2 L1 whole square. Equation 4. Two lines with direction ratios A1, B1, C1 and A2, B2, C2 are number 1. Perpendicular, that is if theta is equal to 90 degree, by equation 1 A1 A2 plus B1 B2 plus C1 C2 is equal to 0. Number 2. Parallel, that is if theta is equal to 0, by equation 2 A1 upon A2 is equal to B1 upon B2 is equal to C1 upon C2. Now we find the angle between two lines when their equations are given. If theta is acute, the angle between the lines vector R is equal to vector A1 plus lambda into vector B1 and vector R is equal to vector A2 plus mu into vector B2. Then cos theta is equal to modulus of vector b1 into vector b2 upon modulus of vector b1 into modulus of vector b2. If Cartesian form, if theta is the angle between the lines, x minus x1 upon a1 is equal to y minus y1 upon b1 is equal to z minus z1 upon c1, equation 1, and x minus x2 upon a2 is equal to y minus y2 upon b2 is equal to z minus z2 upon c2, equation 2, where a1, b1, c1 and a2, b2, c2 are the direction ratios of the lines 1 and 2 respectively, then cos theta is equal to modulus of a1 a2 plus b1 b2 plus c1 c2 upon square root of a1 square plus b1 square plus c1 square into square root of a2 square plus b2 square plus c2 square. Example 1. Find the angle between lines vector r is equal to 3i cap plus j cap minus 2k cap plus lambda into I cap minus j cap minus 2k cap and vector r is equal to 2i cap minus j cap minus 56k cap plus mu into 3i cap minus 5j cap minus 4k cap. Solution: line L1 vector r is equal to 3i cap plus j cap minus 2k cap plus lambda into I cap minus j cap minus 2k cap. Line L2 vector r is equal to 2i cap minus j cap minus 56k cap plus mu into 3i cap minus 5j cap minus 4k cap. Line L1 is parallel to the vector b1 is equal to I cap minus j cap minus 2k cap. Line L2 is parallel to the vector b2 is equal to 3i cap minus 5j cap minus 4k cap. Let the angle between line L1 and L2 is cos theta is equal to modulus of vector b1 into vector b2 upon modulus of vector b1 into modulus of vector b2 is equal to I cap minus j cap minus 2k cap into 3i cap minus 5j cap minus 4k cap upon square root of 1 plus 1 plus 4 into square root of 9 plus 25 plus 16. Because of modulus of vector b1 is equal to square root of a1 square plus b1 square plus c1 square and modulus of vector b2 is equal to square root of a2 square plus b2 square plus c2 square is equal to 3 plus 5 plus 8 upon root 6 into root 50 is equal to 16 upon 10 root 3 is equal to 8 upon 5 root 3. Therefore, theta is equal to cos inverse 8 upon 5 root 3. Shortest distance between two lines. If two lines in space intersect at a point, then the shortest distance between them is 0. Also, if two lines in space are parallel, then the shortest distance between them will be the perpendicular distance, that is, the length of the perpendicular drawn from a point on one line onto the other line. Further, in a space, there are lines which are neither intersecting nor parallel. In fact, such pair of lines are non-coplanar and are called skew lines. For example, let us consider a room of size 1, 3, 2 units along x, y and z axes respectively. The line JEE that goes diagonally across the ceiling and the line DB passes through one corner of the ceiling directly above A and goes diagonally down the wall. These lines are skew because they are not parallel and also never meet. By the shortest distance between two lines, we mean the join of a point in one line with one point on the other line, so that the length of the segment so obtained is the smallest. For skew lines, the line of the shortest distance will be perpendicular to both the lines. Distance between two skew lines. We now determine the shortest distance between two skew lines in the following way. Let L1 and L2 be two skew lines with equations. Vector R is equal to vector A1 plus lambda into vector B1, equation 1, and vector R is equal to vector A2 plus mu into vector B2, equation 2. Take any point S on L1 with position vector A1 and T on L2 with position vector A2. Then the magnitude of the shortest distance vector will be equal to that of the projection of ST along the direction of the line of shortest distance. If vector PQ is the shortest distance vector between L1 and L2, then it being perpendicular to both vector B1 and vector B2, the unit vector n cap along vector PQ would therefore be n cap is equal to vector B1 into vector B2 upon modulus of vector B1 into vector B2, equation 3. Then vector PQ is equal to d n cap, where d is the magnitude of the shortest distance vector. Let theta be the angle between vector ST and vector PQ. Then PQ is equal to ST into modulus of cos theta. Modulus of cos theta is equal to modulus of vector PQ into vector ST upon modulus of vector PQ into modulus of vector ST is equal to modulus of d n cap vector A2 minus vector A1 upon d ST, since vector ST is equal to vector A2 minus vector A1 is equal to modulus of vector B1 into vector B2 into vector A2 minus vector A1 upon ST into modulus of vector B1 into vector B2 from 3. Hence, the required shortest distance is d is equal to PQ is equal to ST into modulus of cos theta, or d is equal to modulus of vector B1 into vector B2 into vector A2 minus vector A1 upon modulus of vector B1 into vector B2. Cartesian form. The shortest distance between the lines L1 x minus x1 upon A1 is equal to y minus y1 upon B1 is equal to z minus z1 upon C1, and L2 x minus x2 upon A2 is equal to y minus y2 upon B2 is equal to z minus z2 upon C2 is modulus of determinant x2 minus x1, y2 minus y1, z2 minus z1, A1, B1, C1, A2, B2, C2 upon square root of B1, C2 minus B2, C1 whole square plus C1, A2 minus C2, A1 whole square plus A1, B2 minus A2, B1 whole square. Distance between parallel lines. If two lines L1 and L2 are parallel, then they are coplanar. Let the lines be given by vector R is equal to vector A1 plus lambda into vector B, equation 1, and vector R is equal to vector A2 plus mu into vector B, equation 2, where vector A1 is the position vector of a point S on L1 and vector A2 is the position vector of a point T on L2. As L1, L2 are coplanar, if the foot of the perpendicular from T on the line L1 is P, then the distance between the lines L1 and L2 is equal to modulus of TP. Let theta be the angle between the vectors vector ST and vector B. Then vector B into vector ST is equal to modulus of vector B into modulus of vector ST sin theta into n cap, equation 3, where n cap is the unit vector perpendicular to the plane of the lines L1 and L2. But vector ST is equal to vector A2 minus vector A1. Therefore, from 3 we get vector B into vector A2 minus vector A1 is equal to modulus of vector B into PT n cap, since PT is equal to ST sin theta, that is modulus of vector b into vector a2 minus vector a1 is equal to modulus of vector b into pt into 1, as modulus of n cap is equal to 1. Hence, the distance between the given parallel lines is d is equal to modulus of vector pt is equal to modulus of vector b into vector a2 minus vector a1 upon modulus of vector b. Example 1. Find the shortest distance between the lines whose vector equations are vector r is equal to 1 minus t into I cap plus t minus 2 into j cap plus 3 minus 2t into k cap, and vector r is equal to s plus 1 into I cap plus 2s minus 1 into j cap minus 2s plus 1 into k cap. Solution. Line L1, vector r is equal to 1 minus t into I cap plus t minus 2 into j cap plus 3 minus 2t into k cap. Therefore, vector r is equal to I cap minus 2 j cap plus 3 k cap plus t into minus I cap plus j cap minus 2 k cap. Comparing with vector r is equal to vector a1 plus t into vector b1, we have vector a1 is equal to I cap minus 2 j cap plus 3 k cap. Vector b1 is equal to minus I cap plus j cap minus 2 k cap. Line L2, vector r is equal to s plus 1 into I cap plus 2s minus 1 into j cap minus 2s plus 1 into k cap is equal to I cap minus j cap minus k cap plus s into I cap plus 2 j cap minus 2 k cap. Comparing with vector r is equal to vector a2 plus s into vector b2. Vector a2 is equal to I cap minus j cap minus k cap. Vector b2 is equal to I cap plus 2 j cap minus 2 k cap. Vector a2 minus vector a1 is equal to I cap minus j cap minus k cap minus I cap minus 2 j cap plus 3 k cap is equal to j cap minus 4 k cap. Vector b1 into vector b2 is equal to determinant I cap, j cap, k cap minus 1, 1, minus 2, 1, 2, minus 2 is equal to 2 I cap minus 4 j cap minus 3 k cap. Modulus of vector b1 into vector b2 is equal to square root of 2 square plus minus 4 square plus minus 3 square is equal to square root of 4 plus 16 plus 9 is equal to square root of 29. Vector a2 minus vector a1 into vector b1 into vector b2 is equal to j cap minus 4 k cap into 2 I cap minus 4 j cap minus 3 k cap is equal to minus 4 plus 12 is equal to 8. The shortest distance between the lines L1 and L2 is equal to modulus of vector a2 minus vector a1 into vector b1 into vector b2 upon modulus of vector b1 into vector b2 is equal to 8 upon square root of 29. Plane. A plane is determined uniquely if any one of the following is known. Number 1. The normal to the plane and its distance from the origin is given. That is, equation of a plane in normal form. Number 2. It passes through a point and is perpendicular to a given direction. Number 3. It passes through 3 given non-collinear points. Now, we shall find vector and Cartesian equations of the planes. Equation of a plane in normal form. Consider a plane whose perpendicular distance from the origin is d, where d is not equal to 0. If vector on is the normal from the origin to the plane and n cap is the unit normal vector along vector on, then vector on is equal to d n cap. Let P be any point on the plane. Therefore, vector NP is perpendicular to vector ON. Therefore, vector NP into vector ON is equal to 0. Equation 1. Let vector R be the position vector of the point P. Then vector NP is equal to vector R minus D n cap. As vector ON plus vector NP is equal to vector OP. Therefore, equation 1 becomes vector R minus D n cap into D n cap is equal to 0, or vector R minus D n cap into n cap is equal to 0, where D is not equal to 0, or vector R into n cap minus D n cap into n cap is equal to 0. That is, vector R into n cap is equal to D, as n cap into n cap is equal to 1. Equation 2. This is the vector form of the equation of the plane. Cartesian form. Equation 2 gives the vector equation of a plane, where n cap is the unit vector normal to the plane. Let P, X, Y, Z be any point on the plane. Then, vector OP is equal to vector R is equal to xi cap plus yj cap plus zk cap. Let L, M, N be the direction cosines of n cap. Then n cap is equal to li cap plus mj cap plus nk cap. Therefore, equation 2 gives xi cap plus yj cap plus zk cap into li cap plus mj cap plus nk cap is equal to D. That is, Lx plus my plus nz is equal to D. Equation 3. This is the Cartesian equation of the plane in the normal form. Example 1. Find the vector equation of a plane which is at a distance of 7 units from the origin and normal to the vector 3i cap plus 5j cap minus 6k cap. Solution. Normal vector n is equal to 3i cap plus 5j cap minus 6k cap. Therefore, n cap is equal to vector n upon modulus of vector n is equal to 3i cap plus 5j cap minus 6k cap upon square root of 9 plus 25 plus 36 is equal to 3i cap plus 5j cap minus 6k cap upon root 70. Given that the distance of the plane from the origin is D is equal to 7 units. Therefore, the vector equation of the plane vector R into n cap is equal to D, which implies that vector R into 3i cap plus 5j cap minus 6k cap upon square root of 70 is equal to 7. Example 2. Find the distance from the origin of the plane x plus y plus z is equal to 1. Solution. X plus y plus z minus 1 is equal to 0. Comparing the equation with ax plus by plus cz plus d is equal to 0. We have a is equal to 1, b is equal to 1, c is equal to 1. Let the direction cosines of normal to the plane be L, M, N. Then L is equal to a upon square root of a square plus b square plus c square is equal to 1 upon square root of 1 plus 1 plus 1 is equal to 1 upon root 3. M is equal to b upon square root of a square plus b square plus c square is equal to 1 upon square root of 1 plus 1 plus 1 is equal to 1 upon root 3. N is equal to c upon square root of a square plus b square plus c square is equal to 1 upon square root of 1 plus 1 plus 1 is equal to 1 upon root 3. Thus, the direction cosines of the normal to the plane are 1 upon root 3, 1 upon root 3, 1 upon root 3. The distance of the plane from the origin O 0, 0, 0 is equal to modulus of ax1 plus by1 plus cz1 plus d upon square root of a square plus b square plus c square is equal to modulus of 0 minus 1 upon square root of 1 plus 1 plus 1 is equal to 1 upon root 3. Example 3. Find the coordinates of the foot of the perpendicular drawn from the origin to the plane 3y plus 4z minus 6 is equal to 0. Solution. 3y plus 4z minus 6 is equal to 0. The direction ratios of the normal to the given plane are 0, 3, 4. Now, the equation of line L which passes through origin O 0, 0, 0 and parallel to the vector 0, 3, 4 is x minus 0 upon 0 is equal to y minus 0 upon 3 is equal to z minus 0 upon 4. Therefore, x upon 0 is equal to y upon 3 is equal to z upon 4 is equal to lambda. Therefore, x is equal to 0, y is equal to 3 lambda, z is equal to 4 lambda. Let the foot of the perpendicular drawn from the origin to the plane be M. Therefore, for some lambda belongs to R, the coordinates of M is equal to 0, 3 lambda, 4 lambda. Now, the point M lies on the plane 3y plus 4z minus 6 is equal to 0. Therefore, 3 into 3 lambda plus 4 into 4 lambda minus 6 is equal to 0. Therefore, 9 lambda plus 16 lambda is equal to 6. Therefore, lambda is equal to 6 upon 25. Therefore, the coordinates of the foot of perpendicular is equal to 0, 3 lambda, 4 lambda is equal to 0, 3 into 6 upon 25, 4 into 6 upon 25 is equal to 0, 18 upon 25, 24 upon 25. Equation of a plane perpendicular to a given vector and passing through a given point. In the space, there can be many planes that are perpendicular to the given vector, but through a given point P, x1, y1, z1, only one such plane exists. Let a plane pass through a point A with position vector A and perpendicular to the vector n. Let vector r be the position vector of any point P, x, y, z in the plane. Then the point P lies in the plane if and only if vector AP is perpendicular to vector n. That is, vector AP into vector n is equal to 0. But vector AP is equal to vector r minus vector A. Therefore, vector r minus vector A into vector n is equal to 0. Equation 1. This is the vector equation of the plane. Cartesian form. Let the given point A be x1, y1, z1. P be x, y, z and direction ratios of vector n are A, B and C. Then vector A is equal to x1 I cap plus y1 j cap plus z1 k cap. Vector r is equal to x I cap plus y j cap plus z k cap. Vector n is equal to a I cap plus b j cap plus c k cap. Now, vector r minus vector a into vector n is equal to 0. So, x minus x1 into I cap plus y minus y1 into j cap plus z minus z1 into k cap into a I cap plus b j cap plus c k cap is equal to 0. That is, a into x minus x1 plus b into y minus y1 plus c into z minus z1 is equal to 0. Example 1. Find the vector and Cartesian equations of the planes that passes through the point 1, 0, minus 2 and the normal to the plane is I cap plus j cap minus k cap. Solution. That passes through the point 1, 0, minus 2 and the normal to the plane is I cap plus j cap minus k cap. Given that vector A is equal to I cap minus 2 k cap and vector n is equal to normal vector is equal to I cap plus j cap minus k cap. The vector equation of the plane vector r minus vector A into vector n is equal to 0 implies vector r minus I cap minus 2 k cap into I cap plus j cap minus k cap is equal to 0. Equation 1. Cartesian equation of the plane. Take vector r is equal to x I cap plus y j cap plus z k cap in equation 1. X I cap plus y j cap plus z k cap minus I cap minus 2 k cap into I cap plus j cap minus k cap is equal to 0 implies x minus 1 into I cap plus y j cap plus z plus 2 into k cap into I cap plus j cap minus k cap is equal to 0 implies x minus 1 plus y minus z minus 2 is equal to 0 implies x plus y minus z is equal to 3. Equation of a plane passing through three non-collinear points. Let R, S and T be three non-collinear points on the plane with position vector, vector A, vector B and vector C respectively. The vectors vector Rs and vector Rt are in the given plane. Therefore, the vector Rs into vector Rt is perpendicular to the plane containing points R, S and T. Let vector R be the position vector of any point P in the plane. Therefore, the equation of the plane passing through R and perpendicular to the vectors vector Rs into vector Rt is vector R minus vector A into vector Rs into vector Rt is equal to 0, or vector R minus vector A into vector B minus vector A into vector C minus vector A is equal to 0. Equation 1. This is the equation of the plane in vector form passing through three non-collinear points. These planes will resemble the pages of a book where the line containing the points R, S and T are members in the binding of the book. Cartesian form. Let x1, y1, z1, x2, y2, z2 and x3, y3, z3 be the coordinates of the points R, S and T respectively. Let x, y, z be the coordinates of any point P on the plane with position vector vector R. Then vector Rp is equal to x minus x1 into I cap plus y minus y1 into j cap plus z minus z1 into k cap. Vector Rs is equal to x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. Vector Rt is equal to x3 minus x1 into I cap plus y3 minus y1 into j cap plus z3 minus z1 into k cap. Substituting these values in equation 1 of the vector form and expressing it in the form of a determinant, we have determinant x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1 is equal to 0, which is the equation of the plane in Cartesian form passing through three non-collinear points x1, y1, z1, x2, y2, z2 and x3, y3, z3. Example 2. Find the vector equations of the plane passing through the points R 2, 5, minus 3, S minus 2, minus 3, 5 and T 5, 3, minus 3. Solution. Let vector A is equal to 2i cap plus 5j cap minus 3k cap. Vector B is equal to minus 2i cap minus 3j cap plus 5k cap. Vector C is equal to 5i cap plus 3j cap minus 3k cap. Then the vector equation of the plane passing through vector A, vector B and vector C is given by vector R minus vector A into vector Rs into vector Rt is equal to 0, or vector R minus vector A into vector B minus vector A into vector C minus vector A is equal to 0. That is, vector R minus 2i cap plus 5j cap minus 3k cap into minus 4i cap minus 8j cap plus 8k cap into 3i cap minus 2j cap is equal to 0. Intercept form of the equation of a plane. In this section, we shall deduce the equation of a plane in terms of the intercepts made by the plane on the coordinate axis. Let the equation of the plane be ax plus by plus cz plus d is equal to 0, where d is not equal to 0. Equation 1. Let the plane make intercepts a, b, c on x, y and z axis respectively. Hence, the plane meets x, y and z axis at a, 0, 0, 0, B, 0, 0, 0, C respectively. Therefore, A into A plus D is equal to 0 or A is equal to minus D upon A. B into B plus D is equal to 0 or B is equal to minus D upon B. C into C plus D is equal to 0 or C is equal to minus D upon C. Substituting these values in the equation 1 of the plane and simplifying, we get x upon A plus y upon B plus z upon C is equal to 1, equation 2, which is the required equation of the plane in the intercept form. Example 1. Find the equation of the plane with intercepts 2, 3 and 4 on the x, y and z axis respectively. Solution. Let the equation of the plane be x upon A plus y upon B plus z upon C is equal to 1, equation 1. Here A is equal to 2, B is equal to 3, C is equal to 4. Substituting the values of A, B and C in equation 1, we get the required equation of the plane as x upon 2 plus y upon 3 plus z upon 4 is equal to 1 or 6x plus 4y plus 3z is equal to 12. Plane passing through the intersection of two given planes. Let pi 1 and pi 2 be two planes with equations vector r into n1 cap is equal to d1 and vector r into n2 cap is equal to d2 respectively. The position vector of any point on the line of intersection must satisfy both the equations. If vector t is the position vector of a point on the line, then vector t into n1 cap is equal to d1 and vector t into n2 cap is equal to d2. Therefore, for all real values of lambda, we have vector t into n1 cap plus lambda into n2 cap is equal to d1 plus lambda into d2. Since lambda is arbitrary, it satisfies for any point on the line. Hence, the equation vector r into n1 cap plus lambda into n2 cap is equal to d1 plus lambda into d2 represents a plane pi 3, which is such that if any vector r satisfies both the equations pi 1 and pi 2, it also satisfies the equation pi 3, that is, any plane passing through the intersection of the planes. Vector r into n1 cap is equal to d1 and vector r into n2 cap is equal to d2 has the equation vector r into n1 cap plus lambda into n2 cap is equal to d1 plus lambda into d2, equation 1. Cartesian form. In Cartesian system, let vector n1 is equal to a1 I cap plus b1 j cap plus c1 k cap. Vector n2 is equal to a2 I cap plus b2 j cap plus c2 k cap. And vector r is equal to xi cap plus yj cap plus zk cap, equation 1. Then equation 1 becomes a1 plus lambda a2 into x plus b1 plus lambda b2 into y plus c1 plus lambda c2 into z is equal to d1 plus lambda into d2 or a1x plus b1y plus c1z minus d1 plus lambda into a2x plus b2y plus c2z minus d2 is equal to 0, equation 2, which is the required Cartesian form of the equation of the plane passing through the intersection of the given planes for each value of lambda. Example 2. Find the vector equation of the plane passing through the intersection of the vector r into 2i cap plus 2j cap minus 3k cap is equal to 7 and vector r into 2i cap plus 5j cap plus 3k cap is equal to 9 and through the point 2, 1, 3. Solution. The vector equation of the plane passing through the intersection of the planes vector r into 2i cap plus 2j cap minus 3k cap is equal to 7 and vector r into 2i cap plus 5j cap plus 3k cap is equal to 9 is vector r into 2i cap plus 2j cap minus 3k cap minus 7 plus lambda into vector r into 2i cap plus 5j cap plus 3k cap minus 9 is equal to 0. Equation 1. The plane is also passing through the point 2, 1, 3. That is 2i cap plus j cap plus 3k cap. Put vector r is equal to 2i cap plus j cap plus 3k cap in equation 1. We have 2i cap plus j cap plus 3k cap into 2i cap plus 2j cap minus 3k cap minus 7 plus lambda into 2i cap plus j cap plus 3k cap into 2i cap plus 5j cap plus 3k cap minus 9 is equal to 0. Therefore, 4 plus 2 minus 9 minus 7 plus lambda into 4 plus 5 plus 9 minus 9 is equal to 0. Therefore, minus 10 plus 9 lambda is equal to 0. Therefore, lambda is equal to 10 upon 9. Putting the values of lambda in equation 1, we get vector r into 2i cap plus 2j cap minus 3k cap minus 7 plus 10 upon 9 into vector r into 2i cap plus 5j cap plus 3k cap minus 9 is equal to 0. Therefore, 9 vector r into 2i cap plus 2j cap minus 3k cap minus 63 plus 10 vector r into 2i cap plus 5j cap plus 3k cap minus 90 is equal to 0. Therefore, vector r into 18i cap plus 18j cap minus 27k cap minus 63 plus vector r into 20i cap plus 50j cap plus 30k cap minus 90 is equal to 0. Therefore, vector r into 38i cap plus 68j cap plus 3k cap minus 153 is equal to 0. Therefore, vector r into 38i cap plus 68j cap plus 3k cap is equal to 153. Coplanarity of two lines. Let the given lines be vector r1 is equal to vector a1 plus lambda into vector b1, equation 1, and vector r2 is equal to vector a2 plus mu into vector b2, equation 2. The line 1 passes through the point, say A, with position vector a1 and is parallel to vector b1. The line 2 passes through the point, say B, with position vector a2 and is parallel to vector b2. Thus, vector ab is equal to vector a2 minus vector a1. The given lines are coplanar if and only if vector ab is perpendicular to vector b1 into vector b2. That is, vector ab into vector b1 into vector b2 is equal to 0, or vector a2 minus vector a1 into vector b1 into vector b2 is equal to 0. Equation 3. Cartesian form. Let x1, y1, z1 and x2, y2, z2 be the coordinates of the points A and B respectively. Let a1, b1, c1 and a2, b2, c2 be the direction ratios of vector b1 and vector b2 respectively. Then vector ab is equal to x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. Vector b1 is equal to a1 I cap plus b1 j cap plus c1 k cap, and vector b2 is equal to a2 I cap plus b2 j cap plus c2 k cap. The given lines are coplanar if and only if vector ab into vector b1 into vector b2 is equal to 0. In the Cartesian form, it can be expressed as determinant x2 minus x1, y2 minus y1, z2 minus z1, a1, b1, c1, a2, b2, c2 is equal to 0. Equation 4. Example 1. Show that lines x plus 3 upon minus 3 is equal to y minus 1 upon 1 is equal to z minus 5 upon 5 and x plus 1 upon minus 1 is equal to y minus 2 upon 2 is equal to z minus 5 upon 5 is coplanar. Solution. Here x1 is equal to minus 3, y1 is equal to 1, z1 is equal to 5, a1 is equal to minus 3, b1 is equal to 1, c1 is equal to 5. x2 is equal to minus 1, y2 is equal to 2, z2 is equal to 5, a2 is equal to minus 1, b2 is equal to 2, c2 is equal to 5. Now consider the determinant. Determinant x2 minus x1, y2 minus y1, z2 minus z1, a1, b1, c1, a2, b2, c2 is equal to determinant 2, 1, 0, minus 3, 1, 5, minus 1, 2, 5 is equal to 2 into 5 minus 10, minus 1 into minus 15 plus 5 is equal to minus 10 plus 10 is equal to 0. Therefore, lines are coplanar. Angle between two planes. Definition 2. The angle between two planes is defined as the angle between their normals. Observe that if theta is an angle between the two planes, then so is 180 minus theta. We shall take the acute angle as the angles between two planes. If vector n1 and vector n2 are normals to the planes and theta be the angle between the planes, vector r into vector n1 is equal to d1 and vector r into vector n2 is equal to d2. Then theta is the angle between the normals to the planes drawn from some common point. We have cos theta is equal to modulus of vector n1 into vector n2 upon modulus of vector n1 into modulus of vector n2. Cartesian form. Let theta be the angle between the planes a1x plus b1y plus c1z plus d1 is equal to 0 and a2x plus b2y plus c2z plus d2 is equal to 0. The direction ratios of the normal to the planes are a1, b1, c1 and a2, b2, c2 respectively. Therefore, cos theta is equal to modulus of a1, a2 plus b1, b2 plus c1, c2 upon square root of a1 square plus b1 square plus c1 square into square root of a2 square plus b2 square plus c2 square. Note, number 1, if the planes are at right angles, then theta is equal to 90 degree and so cos theta is equal to 0. Hence, cos theta is equal to a1, a2 plus b1, b2 plus c1, c2 is equal to 0. Number 2, if the planes are parallel, then a1 upon a2 is equal to b1 upon b2 is equal to c1 upon c2. Example 1. Find the angle between the two planes 7x plus 5y plus 6z is equal to minus 30 and 3x minus y minus 10z is equal to minus 4 using vector method. Solution. The angle between two planes is the angle between their normals. From the equation of the planes, the normal vectors are vector n1 is equal to 7i cap plus 5j cap plus 6k cap. Vector n2 is equal to 3i cap minus j cap minus 10k cap. Therefore, vector n1 into vector n2 is equal to 7i cap plus 5j cap plus 6k cap into 3i cap minus j cap minus 10k cap is equal to 21 minus 5 minus 60 is equal to minus 44. Modulus of vector n1 is equal to square root of 7 square plus 5 square plus 6 square is equal to square root of 49 plus 25 plus 36 is equal to square root of 110. Modulus of vector n2 is equal to square root of 3 square plus minus 1 square plus minus 10 square is equal to square root of 9 plus 1 plus 100 is equal to square root of 110. Hence, cos theta is equal to modulus of vector n1 into vector n2 upon modulus of vector n1 into modulus of vector n2 is equal to modulus of minus 44 upon square root of 110 into square root of 110 is equal to 44 upon 110. Cos theta is equal to 2 upon 5. Therefore, theta is equal to cos inverse 2 by 5. Example 2. Find the angle between the two planes 3x minus 6y plus 2z is equal to 7 and 2x plus 2y minus 2z is equal to 5. Solution. Comparing the given equations of the planes with the equations a1x plus b1y plus c1z plus d1 is equal to 0 and a2x plus b2y plus c2z plus d2 is equal to 0. We get a1 is equal to 3, b1 is equal to minus 6, c1 is equal to 2, a2 is equal to 2, b2 is equal to 2, c2 is equal to minus 2. Cos theta is equal to modulus of a1 a2 plus b1 b2 plus c1 c2 upon square root of a1 square plus b1 square plus c1 square into square root of a2 square plus b2 square plus c2 square. Cos theta is equal to modulus of 3 into 2 plus minus 6 into 2 plus 2 into minus 2 upon square root of 3 square plus minus 6 square plus 2 square into square root of 2 square plus 2 square plus minus 2 square is equal to modulus of minus 10 upon 7 into 2 root 3 is equal to 5 upon 7 root 3 is equal to 5 root 3 upon 21. Cos theta is equal to 5 root 3 upon 21. Therefore, theta is equal to cos inverse 5 root 3 upon 21. Distance of a point from a plane. Vector form. Consider a point P with position vector A and a plane pi1 whose equation is vector r into n cap is equal to d. Consider a plane pi2 through P parallel to the plane pi1. The unit vector normal to pi2 is n cap. Hence, its equation is vector r minus vector a into n cap is equal to 0. That is, vector r into n cap is equal to vector a into n cap. Thus, the distance O and dash of this plane from the origin is modulus of vector a into n cap. Therefore, the distance PQ from the plane pi1 is ON minus ON dash is equal to modulus of d minus vector a into n cap, which is the length of the perpendicular from a point to the given plane. Cartesian form. Let P, x1, y1, z1 be the given point with position vector a and ax plus by plus cz is equal to d be the Cartesian equation of the given plane. Then vector a is equal to x1 I cap plus y1 j cap plus z1 k cap. Vector n is equal to ai cap plus bj cap plus ck cap. Hence, from note 1, the perpendicular from P to the plane is equal to modulus of ax1 plus by1 plus cz1 minus d upon square root of a square plus b square plus c square. Example 1. Find the distance of a point 2, 5, minus 3 from the plane vector r into 6 I cap minus 3 j cap plus 2 k cap is equal to 4. Solution. Here, vector a is equal to 2 I cap plus 5 j cap minus 3 k cap. Vector n is equal to 6 I cap minus 3 j cap plus 2 k cap and d is equal to 4. Therefore, the distance of the point 2, 5, minus 3 from the given plane is modulus of ax1 plus by1 plus cz1 minus d upon square root of a square plus b square plus c square is equal to modulus of 2 into 6 plus 5 into minus 3 plus minus 3 into 2 minus 4 upon square root of 6 square plus minus 3 square plus 2 square is equal to modulus of 12 minus 15 minus 6 minus 4 upon square root of 36 plus 9 plus 4 is equal to 13 upon 7. Angle between a line and a plane. Definition 3. The angle between a line and a plane is the complement of the angle between the line and normal to the plane. vector form. If the equation of the line is vector r is equal to vector a plus lambda into vector b, and the equation of the plane is vector r into n cap is equal to d, then the angle theta between the line and the normal to the plane is cos theta is equal to modulus of vector b into vector n upon modulus of vector b into modulus of vector n. And so the angle phi between the line and the plane is given by 90 minus theta, that is sin 90 minus theta is equal to cos theta, that is sin phi is equal to modulus of vector b into vector n upon modulus of vector b into modulus of vector n, or phi is equal to sin inverse modulus of vector b into vector n upon modulus of vector b into modulus of vector n. Example 2. Find the angle between the line x plus 1 upon 2 is equal to y upon 3 is equal to z minus 3 upon 6 and the plane 10x plus 2y minus 11z is equal to 3. Solution. Let theta be the angle between the line and the normal to the plane. Converting the given equations into vector form, we have vector r is equal to minus I cap plus 3k cap plus lambda into 2I cap plus 3j cap plus 6k cap, and vector r into 10I cap plus 2j cap minus 11k cap is equal to 3. Here vector b is equal to 2I cap plus 3j cap plus 6k cap, and vector n is equal to 10I cap plus 2j cap minus 11k cap. Sin phi is equal to modulus of vector b into vector n upon modulus of vector b into modulus of vector n. Sin phi is equal to modulus of 2I cap plus 3j cap plus 6k cap into 10I cap plus 2j cap minus 11k cap upon square root of 2 square plus 3 square plus 6 square into square root of 10 square plus 2 square plus 11 square is equal to modulus of 20 plus 6 minus 66 upon square root of 49 into square root of 225 is equal to modulus of minus 40 upon 7 into 15 is equal to modulus of minus 8 upon 21. Sin phi is equal to 8 upon 21. Therefore, phi is equal to sin inverse 8 upon 21.